Hello everyone, just a quick one I hope. I hope I don't start babbling on like I usually do. My last video on the calipers, I was trying to find a decoder for pulse view. So what I've done is I've written my own. So if we go to my repositories, I've done a decoder for pulse view. Basically, you go here, you copy this folder. It has two files inside. These two files. You just copy that folder into the decoder folder of pulse view, and you then should be able to use these. So if we just open pulse view. I've connected it up to my calipers. I've also connected the oscilloscope, so you can see the signal comes from the pulse view, from the calipers. Well, one thing I just need to make sure that you're aware. This decoder decodes the inverted signal from the calipers. The calipers are only sending a signal at about 700 millivolts. So what you need to do is you've got your calipers and you've got a signal coming out. What you need to do is run it through two transistors so that you can increase the logic voltage to, say, 3 volts. This is what I've got here, 3 volts. This is the circuit. So we come in with the clock and the data signal, and this bumps it up onto these two pins here, which is what I've got my oscilloscope attached to now, to give me roughly well, what's it say there, 3.8? Well, actually, no, that's the peak. So, well, we've got 2 volts, yeah, 2, so we've got 3 point something there. So, yes, so but doing this actually inverts the signal from the calipers, so you just need to be aware that my decoder decodes the inverted signal from the calipers. Right, so I've said that. Let's go and have a look. Yeah, so basically, well, it's here. You need to just put which lead is on which. You should be able to find it once you've put it in the decoder folder. If you just type in Calliper, it's Calliper with 2 L's. So I've named it Calipers CN for the Chinese, the basic Chinese, the basic Chinese protocol. Basically, the info here, but yeah, you need. It's quite a fast signal, so you'll need to be sampling at least 1 megahertz. Let's get 2 megs of samples. Get rid of that. We don't need that. And let's grab some data. So yeah, so this is what I've written. It explains it a bit more. So if I zoom out on my oscilloscope, you can see that it pretty much looks like what we're seeing down here. So this is the clock. It's not I2C. Don't get confused. SCL stands for serial clock, and SDA stands for serial data. It can be on I2C. It can be on this. It can be on other things. So that's our 2 lines. And then we zoom in to one of them. So like I say, if we zoom in on this one, and It should look similar to this. I'll just move that across a bit. There we go. Can I get it all in? Oh yeah, I think I've got it all in there. Well, basically. So yeah, let's just zoom in so we can look at a captured one, and it should look pretty much the same as that there. Well, I've got this one up there. Let's just make that like that. Oh, shit. There we go. There, it looks like that now, doesn't it? Sort of thing. This one keeps changing because it's live, but this one here, this is a captured piece. So yeah, so what I've done is you've got the null state, that's the bit between between bursts, and then you've got these two frames which we've got here, which you have two 24 bits. So this one now actually converts. So what happens is we're coming in least significant bit first, so you've got your least significant bit here. This is our least significant bit, and then it goes up, and then our most significant bit will be at the other end. Let's get a pointer. Yeah, there we go. So at least significant comes in, and then you end up with your most significant bit here. So what you have to do is, what this does, it actually swaps them around there. So you can see down here where we've got all the zeros at this end here. Look, they're all the zeros at that end now. So so it reads as you would read a binary file, 24-bit binary file. And so you can see there we've got one, two, three zeros, then a 1. So we've got 1, 2, 3 zeros and a 1. Then we've got 2 zeros and a 1. So then 2 zeros and a 1. So you can see this is flipped. So it's showing what's coming. What happens is we have our clock cycle here, and then we have a bit pulse. So every bit pulse, what it does, it reads the data line. So whatever the data line state is during a bit pulse, it will convert to either 1 or 0. So this is low, so we get a 0. Then when we get this bit pulse, you can see actually that is wrong, because I'm going to have to look at it. The edge is so close, it's actually picking this edge, and I should have actually picked that. So I might have to just alter my code. Let's have a look at another. What was that? That was the second one, wasn't it? Hang on. No. What? I thought we just looked at... I'll have to rewind this video. Because I thought we were looking at the... Oh yeah, it was that one there, wasn't it? Yeah, sorry. Yeah. Yeah, that's reading that. So it was the second pulse. Right, hang on. Let's go to another one. Let's try this one. What is that second pulse? Yeah, that's reading that. No. That doesn't quite look right, that. I would have to pick one, wouldn't I? Oh right, yeah. Anyway, these are the least significant bits anyway, so you won't really notice. But yeah, it's something I need to address, is that, yeah. Right, so this time we're all high, 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 and then we're low. There should be a distance like that. I might have to just increase this to sort of like 2 megahertz to get it right, and then do a run. Basically, we'll get less bits, like, but it'll be more accurate. You can tell how accurate you're going to be is by counting how many dots there are in there, but this is more like it, and it overlaps, which is how it should be. So having a sample rate too slow, you can get areas on the edge anyway. Anyways, I'm rambling, and I wanted to make this a quick one. So yeah, it converts each pulse on into a bit or a high or low bit. Then it converts it into a binary by flipping those bits around, and it also gives you an actual decimal value. And then what it does, it also does the conversion, so it converts that decimal raw value into an actual either millimeters or inches. This first segment is for the calibration frame, so this frame is actually, I just convert this to inches, whereas the second frame is actually what you're reading on your dial on the calipers. So what you're actually reading here is the actual measurement on the calipers. So you can see that it says minus 5.95 and it's 0.00234 inches. So this does also the conversion, because this number here is actually the caliper unit. Yeah, it's a caliper unit. So you can see that it doesn't. Well, you've got to sort of multiply and divide by so much to get your actual either millimeters or inches. Anyway, so that was it. I just wanted to say that I decided to write my own decoder for pulse view. So if you've got a digital analyzer and a pair of these calipers, you can now see what's actually happening, unlike the other video. I hope that was of some interest to somebody. It's on my Git page, so yeah, just go there and download it, put all the information there. Right, yeah, that was a quick one. Catch you later, guys.